Welcome everyone. This talk is about seeing what programs do, seeing how they execute, really seeing what happens inside of them. And I will begin by explaining what I really mean by that. And after that we will look at a practical example. There will be some live coding, so I hope you can see it in the back. If not, please come forward. And I really want to show how easy it is to make simple tools that allow us to look inside our programs. And then we will look at how to scale these techniques to performance-intensive programs and larger programs. And I will conclude with an actual practical tool that I've been working on for the last couple of months or so to actually try to use this in a production code base. But so what do I mean by this seeing? Well, when developing for the browser, some parts of writing a program are already really visual, right? You can open your developer tools and you can see the structure of the HTML. You can really look at how the page is structured. You can start changing CSS values and see the effect of this immediately. It's all very visible, even though this is not really something that the end user would do, but it's really useful to us as developers. But when doing web development, we also have JavaScript, right? And we don't really have the same introspection capabilities for JavaScript. We have all these objects and variables and values and callbacks, and we can look at the code, we can see how the code is structured, but we don't really see what's going on once we start running the program. It just does something, but we can't really see what's going on inside. And we can take these little peeks into our system, right? So, for example, we can maybe look at the network tab and see some requests that we make and how the server responds and so on. And maybe we can open the console, right, and start calling some functions. And we can sort of take this peek into the system, trying to see what happens if we call a function, what it returns, and so on. And maybe we can set a breakpoint somewhere, right? We can use the debugger and pause the program at a certain point in time, step through it. It's very local, but it gives you some insight in what's happening right there. But we don't really get an overview of everything that's happening, really a real insight into how our program executes. So you might wonder, why would we want to do that? Right? Why do we need all these silly graphics or visualizations in order to write good code? Well, one reason, I think that there are various reasons, but the most obvious one, I think, is debugging. Because when you have a bug in your program, something is happening in your program that is different than what you imagined it would do, right? So you have a representation of the program in your head, and the actual program is doing something different. And the only way to resolve this is to get data from the program into your head somehow and see where this difference is. And for this, we need to do this in the most efficient way possible, right? We need some sort of user interface, some sort of visualization that our eyes can see and that our brain can easily parse, so that we can understand how our program works quickly. So how do we do this today? Well, often using like print statements, or in the browser console.log, right? We insert them in our program to see what's going on, what the values of variables are at different points in time, which parts of the program are being reached, in what order. But it's a lot of work. So what do we need to do, right? First, we need to be able to reproduce the problem, right? And then we come up with some sort of hypothesis of why the program is doing what it's doing, why it is wrong. And once we have this hypothesis, we need to get the data to actually verify this hypothesis. And we add console.log statements, and this is called instrumentation, right? Adding measuring instruments to our program. And then we trigger the error again, so that we actually run the program. And we get back some data, and in the data there are some clues, right? So maybe it does what you expected, and you have to form another hypothesis, or maybe something is wrong, but you still don't know quite what it is. And so often you have to go back, form a new hypothesis, instrument the program again, trigger the error again, look at the data again. And so this is a very long feedback cycle until at some point you've found it and you can fix your bug. But why do we need to do this in the first place? It is not like we're trying to understand some sort of complex physical system where setting up an experiment is really hard, right? Where we have to control all the variables and make sure that we measure very precisely, come up with a good formal hypothesis, all that stuff. Everything that the program is doing is happening in this computer that we have here. All the values, all the data that we could possibly care about, it's all going through the memory and the processor at some point in time, right? So why can't we just know all this stuff? It is our system, like we are the gods. We should be omniscient. And the technique that I'm going to talk about today is actually called omniscient debugging. And it means that everything is always logged. And this giant log is called an execution trace. And it contains all the data that you could possibly want in order to understand how the program works. And you can somehow visualize this. So how does debugging work with this? Well, first of all, we don't have to instrument things ourselves, right? Because everything is always logged. And since we don't have to instrument every time we come up with a new hypothesis, we can just run the program once and we get all the data, so we don't need to re-trigger the error all the time. And if you have a really good omniscient debugging system, you even don't need to reproduce the problem in the first place, because you can just download the execution trace from the client on which it happened, right? So you're really left with the real problem-solving tasks, looking at forming hypotheses and looking at the data. And I think that with the right visualization, this can happen in a very short feedback loop. While you're looking at the data, your brain can scan it, trying to find patterns, looking for anything out of the ordinary. So that's sort of the theory behind it, but let's actually write some code, right? So the main points that I want to make today is how easy all of this stuff is. So I'm just going to use JavaScript as an example. This might be like some silly loop deep down in a larger application. It's very contrived, but I will show you how to do this for actual applications later. Right? So we have this visualization where after each variable declaration you have this little spark line of how it changes over time. Right? Very simple. And I'm not going to show you how to actually draw lines. I'm using React with SVG in this case, but I'm going to show you how to actually get the data to draw those lines. Right, so that's what we're going to do. And the way that we're going to do that is we're going to transform the program into another program that has all this instrumentation added. So instead of adding console.log commands ourselves, we use the computer to do that. So let me show you what that looks like. I have some built-in commands. Let me first print the program itself. So I can do log left of get program. And now I just have the program as a string here. And I'm going to use a library called Falafel. It's pretty old, but it's really simple to use. And what it does is it will parse the program and it will walk the abstract syntax tree, and you can transform any node in the program. So this is what that looks like. So I call Falafel on this thing with some walk function. Now I need to define a walk function, and it takes some node. And then I just need to serialize this back to a string. And now we have our original program again, but this walk function gets called, and we can see what it does. So I can do something like this, right? So here are all the node types that we're walking over. The first one is an identifier, that's this letter A here. And we have a literal, that's this number 1. Variable declarator, that's this whole thing here. Variable declaration, that's the entire line. And the identifier here is this I again, and so on and so forth. So what we want to do is every time we see a variable declarator, we also want to initialize a tracking variable in the same scope that we can use to track how the variable changes over time, right? So I'm just literally going to do that. I'm going to say, okay, whenever we have a node of type variable declarator, then we're going to update that node and change it. Right, if I just do this, you see that they actually disappear. So I need to put in the original source again, like this. But now I can add some sort of suffix, right? So what are we going to put in this suffix? Well, we want to initialize this tracking variable, and I'm going to prefix it with log, and then the name of the original variable. So I can do node.id.name. So now I have a log A and a log I here. And what are we going to initialize our tracking variable with? Well, we want some sort of object here, right, with a line number and an array of values. So let's just do that here. So I can add a line number here, and I need to add something for that. I can say the nodes.location.start.line, and then I also need to tell Falafel to actually track those line numbers, and I do that like this. And now we have our line numbers here. And so the next thing is to initialize this array of values, right? So let's also do that. So what are we going to say here? Well, we want some values array. And we actually can initialize it with its initial value already, right? Because A has been declared here and I has been declared here. So I can just plug in this node.id.name here. And here we have our initial values array initialized. Make sense so far? What I want to do now is I want to gather these objects into this big array. And for that I'm going to prefix the program that we get here with some string. So I'm going to call this program. And actually, let me do this. Now I can add some string in front of it. Right? And so I'm going to add a window.log, which is just an array. And then I'm going to create a helper function, which I'm going to call start logging. And it just takes an object, and it pushes this object onto window.log, and then it returns it. Right? And now what we can do is we can just wrap all of our objects that we create here into the start logging function. And now since it returns the function, it returns the object, like the original behavior of assigning it to these tracking variables is still there, but we also add a reference to the global log. Sorry? Oh, sorry. Thank you. We would have found out that soon, but this is much better. So now we can actually run the program, right? So I can call save eval. Save eval is just a regular eval, only it makes sure that my laptop doesn't crash if I make a mistake. And now we can actually see what this window log looks like, right? So I can do log write of window.log, and there's stuff in there. Great. And we can actually already plug this into this render sparklines function, right? So I just move this down, plug this window log in there, and we already have a very basic version of this stuff. Right, so the line numbers change if I move this. If I change this initial variable, it will change. I can even add a string here, right? Because my visualization supports that, right? So the only thing that's left to do is actually keeping track of whenever a variable changes. So how do we do that? Let's look at the node types again, right? So here we change a variable, and here we change one, and those are actually both assignment expressions. So here in both cases we have an assignment expression, and we can just do the same thing as before, right? So we can say, okay, well, if we have a node of type assignment expression, let's update it with the original node source and some sort of suffix. Let's stop evaluating for a second here, otherwise I get a lot of errors. And let's look at the program. Right, so now I have some sort of suffix here after each assignment expression. So what do we put here? Well, we want to access our tracking variable again, which is prefixed with log. And then in this case, it's nodes.left.name, I believe. Yeah. And we want to do something with it. Well, we want to access the values array, and we want to push something to it. What do we want to push to it? Well, just the node.left.name again, right? Because it has just been updated. So we push it to it, and this is pretty much it. Right, so I can evaluate my program again, and now I have working sparklines. And so let's just play a little bit with this, right? Like see what happens if I do this, right? What happens if I change this? What happens if I remove the minus sign? Just think about that for a second. Right? And since my visualization supports strings as well, I can also do something like this. And this is actually interesting already, right? Because the way that I draw these dots here is that the y-axis, the y-coordinate is determined by the length of the string. And if you notice, there's like this little jump here, right? Because here we are adding the same number of characters to the string, but here we're adding a different number of characters. And so your brain can immediately spot patterns like this, right? And so I would imagine that even for more complicated things like objects or so, where we could invent some sort of representation, visual representation of it, even though it doesn't necessarily have to make a lot of sense always how it is represented, as long as you can recognize certain patterns in it, it's easier to spot anomalies. And this is just one visualization, right? There are visualizations out there that actually seem to help you find problems much faster. And some estimates say that about half of a programmer's time is spent debugging. So making just this easier would already have a pretty big impact. And I think that visualizations like this are not just useful for debugging, but for writing new code too. Yeah, so now you might think, this is like a nice small example, but how does this impact my actual production application? Like especially if you have something very performance intensive, all this added instrumentation, it does add a lot of overhead to running your program, and this execution trace that you get might be huge, so it might take a lot of memory. And these are good points, but they can be solved. And I will show you now a project that I worked on not too long ago. This is an educational programming course, and I wanted kids to be able to make their own games, which they really like, but having a great editing environment to do so, right? To really immerse them in this editing environment where they can understand how programming works and how their program executes. So for this, I had to implement some tricks to fix this problem of performance, because even a simple game like this is already relatively performance intensive. So let me first show you what this environment can do, so that you have a sense of the issues. So actually, this seems to be kind of off. Let me just refresh this to see if I can get this right. There we go. So first of all, you can just change stuff here, and it automatically like hot reloads, right? This is not a visualization yet, but it is also kind of important in order to be able to do things like this. What is a visualization though is this pause button, right? And so you pause the program, you can go back in time, and so here we're already looking at previous states that the program had. And we can inspect any one of these states and see, for example, where this ball is being drawn, where these bricks are being drawn, what this function draws, well, all the bricks. I can move my mouse over this one here and get an abstraction over time. All these ideas are taken from previous work. So I can I can do all these things, and then I also have a sort of raw view into the execution trace at the bottom here. So if I move my mouse over here, I can really see step by step what the program is doing. Each statement, but also like intermediate expressions. I can see exactly what's going on. So how does this work? Well, first a paddle is being drawn here, then maybe at some point this, the ball, and then we are redrawing all the bricks, right? So now I kind of know how this program works. It might not be very efficient to like redraw all the bricks all the time, but that's very easy to spot this way. So how do you make something like this efficient, right? And the trick is that if I press play again, that the visualizations go away, right? So while the program is running, oftentimes you don't need to see all this information because so much is changing so fast anyway. So in theory, we could now be running our original program without all the instrumentation. But how do we get stuff? How do we get all the visualizations when we press pause? That trick is in two parts: snapshotting and deterministic replay. Those might be familiar topics at this conference. So how this works is every once in a while the system takes a snapshot or checkpoint, I've also heard it called, of the entire system, right? So it makes a copy of all the variables in memories, all the objects, and it takes a copy of the canvas here. But it only does that once in a while. Like it doesn't take that much space or degrades performance that much, at least not as with the full execution trace. And then when we pause the program, we just go back to an earlier snapshot and we rerun the program, but this time with all the instrumentation. And the only way that we can do this is if we make sure that when we replay the program, it is executing in exactly the same way as it did before, right? Deterministic replay. And that's not always the case because you have callbacks to the server and math.random and things like that. And so while the program is running originally, you also have to store all these sources of non-determinism so that when you play it back, you can fill them in and make sure that it runs in the same way again. And so that adds a little bit of overhead too, but still it's much, much less than the full execution trace. So it takes a little bit of bookkeeping, and it's kind of hard to do, but luckily people have done this for us. There's a project for WebKit called Timelapse. It's an academic project, and it has been done a couple of years ago, so I don't know its exact status now, but it doesn't have a lot of overhead, and it allows you to do this, well, basically with any visualization that you come up with, right? Because a system like this is independent of the particular visualization or instrumentation that you add. So now that we have seen like tools like this, it was still a pretty contrived example in the beginning, and this was an educational environment that was also pretty limited. What about real practical tools, right? And there are some out there for various programming languages, not really for the web, unfortunately. So a couple of months ago I started in my spare time just playing around with one of them, and it's actually integrated with the code base for the company of the company that I work for. So I'll give you a quick demo of what something like that would look like. So here's my company website running on my local machine. Just a quick word about my company. I work at this company called Brigade, and we're trying to re-engage citizens in the political process and make it easy for them to take collective action. So this is their homepage, and if you notice, there's this little bar at the bottom here. Let me try to zoom in a little bit. So there's this bar here, and this bar is just a representation of the execution trace. And if I click it, you can see all the events that happen in the system, right? That happen on my on the website, and they're laid out from left to right in the same way as in the educational programming environment, chronologically. And then I use the vertical space to represent the stack depth, right? So every time a function is called, we go one level deeper, and then when it returns, we go up again. And so you can kind of explore what's happening here, right? And I collapse certain branches of the tree so that you don't have of the graph, so that you don't see everything at once. So if we see something interesting here, like I think initialization of the page happens here, like we can drill deeper, right, and see what's going on here. Can you see this? Let me just show it like this. So you can just go through everything that happens, right? I mean, there's no point where we have to call a debugger statement and we can only move forward, and then if you skip over something, like you can't go back, you have to rerun the program again. You can just see, oh, this might be interesting. Right, and every time a function is called, you may notice here that I also log the arguments to that function, so that you can kind of see what's happening. And then there's also this representation here of things in this file that are happening around the same lines. So if I hover over this one, then up here you can see the corresponding events in the execution trace there being highlighted. Right, and just an example of how you can use something like this to understand the program. If I scroll down, you can see that the bar becomes larger and something happens at the top of the screen, right? So let me actually show this on the team page. I think it's a little clearer there. So if we scroll down, this bar at the top docks, right? And if I do that, it goes away again. And we can actually see this very clearly in the execution trace. So here you see all the events being called whenever I scroll, and then here suddenly something happens, right? We see a different pattern and we immediately recognize this. And I can drill down and see, oh, well, we're actually re-rendering the dockable component. So that's what's going on there. It's still all pretty experimental. Oh yeah, there's another feature. I can search for things here. So I'm on the team page here. So if I search for team, I can find out where the team page is initially being rendered. And it's somewhere here. So here the team page is being rendered and all sorts of stuff is happening here, right? So, yeah, this is in a very raw form online. If you're interested in like hacking on this or like in this about this stuff in general, come talk to me afterwards. But just to recap, with HTML and CSS, we can really already see what the program does, but with JavaScript, we are blind, essentially. We try to see using console.logs and debugger statements, but we should really be omniscient, right? We are in control of our machines. And tools to become omniscient are surprisingly easy to make, like I did this in 10 minutes. And once you have them, you can scale them to larger systems. There are tools out there even for the browser to do that. And you can actually like build a practical tool like this in a couple of weekends with a real code base. And it kind of works. So you can find more background information on this page. I don't know how much more time we have. When does the session end?
1:30, 15 minutes.
Oh, 15 minutes. Yeah, so we have plenty of time for questions. Are there any questions? Oh, sure. Oh, actually, let me do this like this. Yeah, so actually if you go to this page, the GitHub page is linked there too, and there's all sorts of research and other tools up there too. Yes?
What are your thoughts about how a functional programming language might change or leave stories today?
Yeah, so the question is, how does a functional programming language, like how would that work with visualizing it like this, right? That's actually a really good question, I think, because with functional programming languages, at least in terms of all the checkpointing and deterministic replay, it's probably a lot easier to do that. It's also quite interesting to visualize that. Actually, if you go to my site, like not the strange loop one, but just my homepage, there's actually a project where I do that as well. I might link to it from here. That might be interesting too. Yes.
The educational tool that you made for kids to
Yes.
build their own games, did you actually use that with students? And
Yeah.
how did they take the visualization and did they use the feature that you stopped on there to trace like a program around?
Yeah. So I did use testing with that with children from like ages 10 to 18 or something, I believe. Yeah. And it's kind of hard to tell. That particular feature was not very discoverable, but I found it particularly useful when doing like instruction, when showing something to people like, oh, this is what's going on. And I think I've seen like some children use it with the other features that I showed, where you can move your mouse over things and like things light up. It's really hard to see if they're using that, because people just move their mouse around and like stuff happens. They definitely use the scrubbing of values, and that was, I think, helpful. But yeah, it was really hard to tell if they were using those features. I think in general, like the course worked pretty well, but then again, I also like made the exercises and such, and so I don't know what I can attribute to this editing environment and what I can attribute to the actual exercises that I came up with. So yeah, I don't know exactly. Yes?
It looks like there's a little bit of crossover with what I've seen a few other people doing in the sort of React hot loading space.
Oh yeah.
You've seen like the Redux time travel sort of stuff.
Yes.
Have you integrated what you've got with those sorts of environments?
This is actually compatible with React hot loading, because we use that in our code base as well. We don't use a Redux system. A Redux system would be that would integrate with something like this very nicely, I would imagine. Yeah, so I think that there's obviously like a lot of crossover also with the functional programming language. And there are like entire languages that, like Elm and such, right? That this would work, I think, very, very nicely with. Yeah. Yes.
I'm curious where this fits in for you with unit testing. I mean, do you find that this takes the place of some unit tests, or they go alongside each other?
Yeah, so the question is, how does this like work with unit testing? Does it replace unit testing, or does it go alongside with them? I don't think this would really replace unit testing, because like unit testing gives you certain guarantees of how your program executes, and this just gives you insights. So you don't necessarily, if you change something, notice that your program actually behaves like in an incorrect way very easily. But I have found that when trying to debug a unit test, like it's the same as when trying to debug like an actual problem in the application, that it's pretty helpful. Like all this stuff also just runs in our Jasmine specs, and I've used it like that a couple of times. Yeah. Yes?
Did you at where you're using this work, have you noticed has there been like a noticeable increase in productivity?
This is an excellent question, because I meant to say something about that, but I forgot. So the question is, have I actually noticed an improvement in developer productivity when using this? And the answer is not yet, but I've only been working on this like for like 2 months or something. So the way that it has gone so far is that I try to use it, and sometimes it was useful, but sometimes I'm like, oh shit, I need more data, or like I need a search function, or I need this, or I need that. And I would write that down, and in the weekend I would make it, and then like the next week I would try some things again and like make notes of everything that I ran into that time. Yeah, so I'm not quite sure yet. I hope it does. Like the academic research that people have done into tools like this suggests that it might, but I don't know yet. No more questions? Thanks a lot.